Okay. Now, given what the energy, this is by how much it splits, because you have a doublet, right? You have two energy levels, two frequencies of the light of the photons being generated, whereas before just one. Okay, and the difference in the energies is this amount. So this is from earlier theory, a few sessions back. Okay. Now, so you had an original energy level, let's say it's here, and then the spin orbital splits it, so one line will go up and the other one will go down. And in the case when it goes up, when J is 3/2, it goes up by this amount, right? And you can plug that in. If J is 3/2, you just put that into here. L is 1, I guess, and S is plus a half, okay? Well, we could do that almost now, right? I won't bother with it. Okay, so you plug that into there, make that 1, make that a plus a half, and you'll come out, I guess it's just 1. Does that make sense? That's 2, what is this? That's 5/2 times 3. If you're good at mental arithmetic, okay. Anyway, so it just comes out, this comes out as 1, right? Now when J is a half, so L's at 1 again, so S I guess is minus a half. It comes out as 2. Does that make sense? Right, so it goes down. All right. So the difference between this. So this one goes up by this much, goes down by double that. So the difference between the two will be 3 times this. Okay? So 1 up and 2 down. The gap between them will be 1 plus 2. So, all right. And calculating what the expectation value for F is for hydrogen. In fact, we did that in an earlier session, right? So that you can you can calculate these energy splittings for hydrogen. All right. All right. Now's the time. The 2 sessions back were one session back. We're looking at the splitting of energy levels in the spectrum due to the presence of a magnetic field, the Zeeman effect. Okay. So now we've arrived at what we were there talking about the future. Well, the future's now, right? So as your magnetic field gets switched on, so it's no longer 0, right? Then you get all this splitting of the allowed energy levels. And I was mentioning this in the previous session. If you have a strong magnetic field, the gaps become so large between the allowed energy levels, like the lower ones, can then cross over the higher allowed energies due to the lower splitting from the spin-orbit coupling. Right? That's effectively what this is saying. Now, so what happens now is there are various this phenomena, this splitting of the spectral lines. You can analyze it into various categories in the following sense. Various cases, I suppose, probably a better way of expressing it. One case is when the magnetic field is very strong. Okay, so when that's the case, you can neglect other terms as negligible and so forth. It simplifies the mathematics. So for this in the next session, we will talk about 3 different cases. Right. So the first one is when the field is strong. Okay, so the strong field Zeeman effect, and the second one, you can't see it. It'd be the next session, but I'll just tell it. It's something called the Paschen-Bach effect. And in the first one, the field's strong enough that you can just neglect the spin-orbit term. In other words, the third term in the Hamiltonian from 2 sessions, well, session back. Okay. Now, in the second case, the so-called Paschen, P-A-S-C-H-E-N, Back, B-A-C-K, two physicists. You do not neglect the spin-orbit coupling term. Okay, so it makes things more complicated. So that's what's like the second case. And the third case is when the Zeeman effect comes from a weak magnetic field. So for this, well, the remainder of this session, the next one, and a bit the one after that, and then we're at the end of the chapter for the theory session, theory part of the chapter. Effectively the rest of this lecture is about these three cases for the Zeeman effect. Right? Okay, so this is a strong case, a very strong magnetic field, and so the separation, the gaps, the energy gaps between the splitting of the frequencies, the allowed energies of the eigen energies. So assume it's strong enough. Okay. So the spin-orbit term is neglected. So just remove the third term in your Hamiltonian. But it warns you it can't be too strong because the because sign here. Because if it is too strong, if it is very strong, then we'll go back a session ago. If it's very strong, then remember the ratio of the quadratic term of the interaction energy of the Zeeman effect divided by the linear term. It was something of 10 to the minus 6 of the magnetic field strength, B. So 10 to the minus 6 times B. Well, if B is very large, that 10 to the minus 6 may not drown it out. Right? If B is really huge. And that's possible in, like I was saying earlier, in certain circumstances in astrophysics. I mean, like the magnetic fields of the sun, of stars, just enormous, right? So unless you're dealing astrophysics, well, you shouldn't allow your magnetic field to become too strong, because otherwise then you cannot ignore the quadratic term, which changes all the mathematics, makes things a lot more complicated. But strong enough to neglect, just allow to drop out the spin-orbit term, so the third term in your Hamiltonian, okay? But not so strong that the 10 to the minus 6 times B becomes non-negligible, right? Okay, so, and this neglect, the dropping out of the third term is thought to be reasonable in labs, because the strength of magnetic fields that you can generate in the lab are nowhere, nothing like that. Well, I think I put numbers. Let me see if I can. Yeah, so more or less typical maximum magnetic field strengths in the lab are less than about a kilotesla, a KT, capital T, Tesla, a unit of magnetic field strength. Okay? Right? Okay, so the third term drops out. Now, with that approximation to the strong magnetic field, then the Hamiltonian commutes with these four operators. And that means that, remember, if some operator commutes with H, then its corresponding eigenvalues are conserved. Remember that? Quite a while back, from quantum mechanical theory. Okay. Now, therefore, these four operators here, angular momentum squared, spin squared, the z component of angular momentum, the z component of spin, all four of those operators, they all commute with H. Now, H now with the three terms, the H naught, the L squared, the third term's neglected, and the fourth term, the Zeeman term. Okay. So that Hamiltonian commutes with all four of these, and therefore the eigenvalues of these four operators are conserved. Okay. They're constant. And I'll just continue straight on the next session.